code to the cloud. All right, so today's lecture is on doing hypothesis testing and interval estimation, but when we have two populations. And I believe I sort of did a little introduction to that topic in an earlier class, but now we want to get a little deeper into it. So the idea being that, excuse me, sometimes we are interested in whether or not there is a difference between two population means. Now we could do the same thing for proportions as well. So say, for example, if we were looking at, say, the average cost of living in two different cities, and we were looking at, say, Montreal and Halifax. So we could be asking, is the average amount that a household of four spends on living expenses, is that different from Montreal compared to Halifax? In that case, we have two populations. If we were only looking at one region like Montreal, we could be hypothesizing about the average amount of money spent by a family of four, right, in terms of living expenses in Montreal or in Halifax. Those could be done separately as what we call single sample problems. But then if we want to now compare two different populations like Montreal and Halifax, or Toronto and Vancouver, then in that case we are looking to compare those two different population means. And typically what we are interested in is whether or not there is a difference between those two population means. So if we call one of them mu1 and the second one mu2, is there a difference between mu1 and mu2? And we could answer that question by getting a confidence interval, an interval estimate, or by getting doing a hypothesis test, all right? So we'll kind of look at those. Now, today's lecture will cover just the difference between means, and then next week's lecture will cover the difference between proportions, because we could ask the same kind of question in terms of proportions if we're looking at two different cities. For example, does Quebec City have a higher proportion of females than, say, Halifax? In which case we would look at the population and would say, oh, Quebec City have 55% females, Halifax have 52. Is there a difference between those? So we would actually take samples and then look at the sample proportions for females in Halifax, females in Quebec City, and then try to find a difference between those two population proportions. So we could be asking that question, is there a difference between the proportion of females and so on? Or we could be talking about things like unemployment rate. So unemployment rate is like a proportion of people who are eligible to work who are not working right now, but who are actively seeking work. So that's a proportion, and we could look at, is that different for Ontario versus Saskatchewan, you know? And so we are also interested in the difference between population proportions. But for tonight, we'll focus on the difference between population means. So let me share my screen. I want you to tell me if you're seeing my iPad. Are you seeing my iPad with interval estimation? Mu1 minus mu2. Are you seeing that?
No.
No?
I can't see it.
Okay. It's saying that I'm sharing a screen, but I am not seeing. I wonder if it's because. Give me 1 second. Unprompted on your iPad. I was not prompted. Let's try a different approach. Just go. Give me 1 second. We'll try this via AirPlay. And here we go. Let's try this a second. My iPad doesn't want to cooperate with me today. Just give me 1 minute, folks. I'm going to see what's going on here. Nope. Okay. Let me see. How to share my screen. I'm going to try something else. Bear with me. Technology is great when it works, and sometimes it could be a pain. Go and try this again. And I'm not seeing anything. I don't know why it's not working this time around. Why is it not working? And we have 105. No. Just me. Try it. Okay, let's see if this works this time. Any luck? You seen my iPad now?
Still can't see it.
Still not seeing it. Okay. Then we'll try. Let me see a new share. Stop share. We'll try one more time. Let's try the AirPlay. And come on, don't do that to me. Okay, well, I'm going to restart my iPad, but in the meantime, we'll just do a PowerPoint version. And then hopefully sometimes you just have to restart these things. So in the meantime, I will try to do a PowerPoint version of the presentation for you. Let me bring that up. And we're going to share screen. Okay, I'm sure you've seen this, my PowerPoint now. You seen my? Yeah. Okay. You seen that? Okay, no problem. And you've seen that full screen as well, right?
Yes.
Okay, great, no problem. Okay, so let's just, what I'm trying to establish. So the idea being that we are interested in the difference between two population means. In this case, we're trying to either hypothesize about these two means, or we're trying to get a confidence interval for the two of them. So if we are trying to get a confidence interval and the two standard deviations are known, then we have the following formula given to us. So these would be, remember that for a confidence interval, they're the following parts. One is that we have to have what we call a point estimate. So when if you recall, when we found a confidence interval for a population mean, just a single population, we had X bar plus or minus either Z or T, and then either sigma or S over the square root of N, right? So that was a single sample case. And we used Z or T depending on whether or not we knew sigma, the population standard deviation, or not. When we did not know the population standard deviation, we used S. We use a T distribution. When we knew the population standard deviation, we use the normal distribution Z. The same idea applies. Now, instead of having a single population where we're considering just X bar, now we're considering X bar 1 minus X bar 2, and that represents the difference between, the sample difference between the two population means. So we don't know what those two means are, but we will actually get two samples, one from each population, and then we will subtract one sample mean from the other, and that is an estimate of the difference between the two means. So for example, if say a family of four spends say $1,600 a month on expenses in Montreal and spends $1,200 a month in Halifax, the sample difference between the two would be $400, the difference between $1,600 and the $1,200, $400. So that's our point estimate of the difference. Now, you recall that the confidence interval have the following form. It has a point estimate, it has a critical value like a Z or T, and it has a standard error. So the standard error, when we are talking about the difference between population means now, so the standard error for the difference between two sample means is given by this formula if we know the population standard deviations. So sigma 1 squared over n1 plus sigma 2 squared over n2, and we take the square root of all of that. So if we are able to do that, that gives us our standard error. So now we have the point estimate, the standard error. The only thing missing is Z or T, which is our critical value. And that critical value, you may recall, will depend on the confidence level. If we want a 95% confidence interval and we're working with Z, the normal distribution, that Z value will be 1.96. If it is a 90% confidence interval, it will be 1.645. So you would have done some examples where you would have calculated those values. So to show you the final formula, so this would be the formula for us to estimate the difference between two population means, between Montreal and Halifax, between Toronto and Vancouver, etc. We would have to get the two samples. This is our critical value, and this is our standard error. Those are the three parts. Excuse me. And so if we know the population standard deviations, it's nice and easy. No problem. I'm just going to, before I try to work up an example for you, I will just try to move to the next formula. So what if we don't know? What if we don't know the population mean and the population standard deviation? Sorry, not the population. What if we don't know the population standard deviation? Sorry, we don't know the population means. That's why we're hypothesizing about it. So if we don't know, sigma 1 and sigma 2 are unknown. Let me just, here's what our confidence interval looks like. It looks very similar to the other one, X bar 1 minus X bar 2. But notice now we've replaced the critical value with the T value, T alpha over 2, which basically means the T value when you have alpha over 2 in the tail of the distributions. And then S1 squared over N1, S2 squared over N2. Notice that instead of sigma, we now have S. There's one little trick to this problem, is the degrees of freedom. It's a horrible looking formula. As you look here, you will see that horrible looking formula below. And so you would have to basically use a calculator, use Excel, and so on to be able to find this degrees of freedom. So the degrees of freedom is with this complicated formula, and it will not be a whole number. So most likely it's not a whole number, so you'd have to round up. So round up to the next degree of freedom in that case. Now, I have actually put this formula in an Excel spreadsheet that I will share with you guys so that you don't have to try to calculate this by hand when you're doing the sample problems. So I am going to I am going to provide you with an Excel spreadsheet that you can use, and then you could feel free to use it in the test as well if that situation comes up where you have to calculate this degrees of freedom. So I will make that available to you on Brightspace. So that's the confidence interval formula when sigma 1 and sigma 2 are not known. And so the degrees of freedom is a crazy looking formula like this. When we want to do a hypothesis test now, we're going to need a test statistic. And if you remember the general form of a test statistic, I'm just going to show you for a hypothesis test, and then we will kind of pull them together. So if we're testing a hypothesis about the difference between two means. So for example, I could test the hypothesis that cost of living in Montreal is higher than cost of living in Halifax. So if we look at this hypothesis right here, notice that what I'm trying to show is that mu1 minus mu2, that's in our alternate hypothesis, is less than a particular value. That value in this case could either be 0 or some particular value. And then, so the null hypothesis, we will hypothesize that the difference is greater than or equal to that value. Always remember that the equal sign is in the null hypothesis. So an example of that case would be that if we believe, say, Halifax has a lower cost of living on average, so we will try to prove that Halifax, if it's lower, minus Montreal, mu2, would be less than 0. And the reason why we say less than 0 is because if mu1 is smaller, that's Halifax, the difference between Halifax and Montreal will be negative because we're subtracting a bigger number from a smaller number, in which case this should be less than 0. And therefore the null hypothesis would be greater than or equal to 0. We could actually switch them around if mu1 represents Montreal in this case. So our alternate hypothesis or our research hypothesis is that the mean cost of living in Montreal is greater than the mean cost of living in Halifax. So mu1 is expected to be larger than mu2. So mu1 minus mu2 is greater than 0. And therefore the null hypothesis is just the opposite of that. But sometimes we're not interested in whether or not one mean is greater than the other or less than the other. We're simply interested in whether or not they're different or there's been a change. Because sometimes we might say, 10 years ago, the average tuition fee was, say, $4,000. Now let's take a random sample of students and find out what the average tuition fees are today. So if we're comparing today with yesterday, then we could ask the question, has the average cost of tuition changed? So in that case, I'm not asking whether or not it has increased or decreased, but whether or not it is no longer the same. In which case, the difference between the two, mu1 and mu2, will not be 0. Because if that difference is equal to 0, it means that they're the same. So what we would be testing is that there's a difference between them. And so that would be a two-tailed test, a two-sided test. And then in the null hypothesis, we'll assume that they're the same. So we'll assume that they're the same, but really and truly what we're trying to show is that they're different. All right? And that's where HA comes in. So that will give us what we call a two-tailed test. So that's the hypothesis test involving the difference between mu1 minus mu2 with sigma 1 and sigma 2 known. The importance of sigma 1 and sigma 2 being known is that our test statistic will be Z, not T. Z. But then now, if we wanted to do the same hypothesis test, but sigma 1 and sigma 2 are not known, then we would have to change the hypothesis to a T, and not the test statistic, sorry, to a T. Let me see if I can find that formula for you. It should now be T. There we go. So the same hypotheses that you saw earlier, but because sigma 1 and sigma 2 are unknown, we will have to use T. But the degrees of freedom that we're going to use is calculated by that crazy looking degrees of freedom formula. All right? So that's the second scenario. The third scenario with difference between population means, and that's the last one that we're going to cover. And after that, I want to work some sample problems for you. I'll try to figure out what's going on with my iPad. So first scenario, we are interested in difference between population means, but the standard deviations are known, so we use Z. Second scenario, interested in the difference between population means, but the standard deviations are not known, so we will use T. Third situation now is a particular case, which we refer to as matched pairs. You see, what happens is that when we are looking at two independent samples to test the difference between two population means, sometimes we could introduce what we call variation between the two different samples. In other words, the sources or the causes of variation between those two, there could be many causes of variation. Sometimes we are interested in an experiment where we want to reduce the number of causes of variation. So let me give you an example. What if I wanted to test a new way of doing work? So a company basically approaches a particular piece of work, like, you know, the creation of a product, in a particular way. New research has shown that if the company changes the process, it could actually do better. It could be more efficient, more productive. So we could say, let us take a random sample of workers and get them to use method 1, the old method, and see how much, in a fixed amount of time, how much product they produce. Then we could take a different group of individuals, so now that makes it independent. It doesn't have to be the same people, and we get them to use method number 2, the new and improved method, and we look at their output and say, is there a difference between those two groups? Well, if we do find a difference, we'll say, is it because of the method? Or is it because maybe group 2 had better workers than group 1? There could be other reasons. Maybe some of the workers in group 2 were sick. And so as a result, group 2 did worse than group 1. There could be other factors, right? So what we do is we try to control for these factors by designing an approach that uses the same people before and after. So what we would do in that case, and that's why we refer to it as matched pairs, what we would do in that case is that we would ask an employee, let's call that person employee 1, to try the old method and see what they produce. Then we'll tell them to try the new method and see what they produce. And now, because you are using the same person, the difference between their production is because of because they're the same individuals in both situations. The only thing that changed was the method. Then you could say the difference in the output is because of the method. All right, so that's the idea. So we've controlled for the person being sick, or some workers are better than others. Because we're using the same worker before and after, then in that case, we have two values given to us by the same person, and we can compare them. And we call those two data values a matched pair. Just like a pair of shoes. The two shoes on my feet are matched because they fit me as the individual. So the value that you would get before the using the old method and the value using the new method coming from the same person means that those two values are matched to that individual. So this is a different kind of experiment that allows us to test the difference between two population means, mu1 and mu2, but we designed the experiment in such a way that the same individuals give us a value for population 1 and a value for population 2. And so as a result, what we then do is we focus on the difference between the scores, and we end up with a single sample Not two individual samples, but a single sample. Let me give you one other example of that situation. Say we wanted to find out whether or not the color of a room influences your attitude towards work. So, if you're in a nice, painted room and so on, bright lights and all that stuff, maybe a off-white or something, that you might be more excited about working and then be more productive. If I gave you kind of a real bright green room, you might say, well, man, I just want to get out of here. You're not really that interested in that environment. It doesn't excite you. So as a result, you might be less likely to be productive in that environment. So if I want to test if there's a difference between the green room and then the bright room, if I took a random sample and put them in the green room and a different random sample, put them in the other room, and then get them to work and then score the attitude towards the room, these are two different groups of people. So those will be considered independent samples. However, if I take the same person and say, you work in that green room for 1 week, and then I'm going to switch you and work in that bright room for another week. And then the other person, you flip it. Now you work in that bright room for a week, and then I'll put you into the green room. So you kind of flip it back and forth because you don't want everybody starting green first and then the bright room second, because the order could skew your results, right? It could be that if you went from that terrible green room to the bright one, you might say, whoa, wow, what a difference. Whereas if you now go from the bright room to the green room, you say, oh no. And that kind of attitude can really mess things up. So you got to kind of scramble it among the different people so that everybody's not in exactly the same order. All right? So that, when we generate those two samples, we call them match pairs. And there are examples with that. So I wanted to do an example of each of those cases for you. And then, so here's an example of match pairs, where inference is about difference between two populations in match pairs. So you have a district office and then delivery time in hours. I'm assuming that this must be a problem about a courier. So from Seattle, delivery time is 32 hours. If you use the company Intex, is 25. So I guess we're looking to see whether or not there's a difference between the delivery time for these two different companies. So Seattle is common to both of them, so those two are match pair. So that would be like your pair of shoes that belongs to this person. Los Angeles, 30 and 24. Boston, 19 and 15. So now that we have these two samples given to us by the same places, we take the difference between them. And if that average of those differences is not zero, that means the difference between the population means is likely not zero as well. Because remember that when we take that average d bar, we call these differences di, and when we average them, we'll call it d bar. That average is an estimate of the difference between the two population means. So the mean for UPX and the mean for Intex. So almost look like UPS and FedEx. Which I suspect is probably what that's there, but they try to hide it. So in that case now, when we get that single sample of values here, it turns out that our problem will result in a single sample problem where we're going to test whether or not the average difference between the two population means, mu1 minus mu2, is zero or not zero or some other value depending on the nature of the problem. All right, and look at what the test statistic look like. The test statistic is T is equal to d bar minus mu d s d over root n. That's the same statistic that we used when we were doing a single population problem with sigma unknown. What we had was T is equal to x bar minus mu s over the square root of n, with the degrees of freedom n minus 1. Well, that's exactly the same thing. Instead of saying x minus mu, we're saying d bar minus mu to denote the average of the differences. And then this is mu, the same population mean difference, So the subscript D is referring to difference. SD is the standard deviation of those differences. So in this problem right here, we would have to calculate the average of those differences and the standard deviation of those differences, which we've done way back in chapter 3. All right. And then with that information, we could then calculate the test statistic, 2.94. And that's actually looking, reasonably high enough and so on. So we could then continue with the steps of the, for the hypothesis testing. So I think what I like to do now to make this a little clearer to you, more solid, is to really be able to do some examples. So let's see if I could get now the iPad situation resolved. So bear with me. In the meantime, if you want to ask me a question to clarify anything when I'm trying to get this to work, do let me know. So I'm going to stop this sharing. Save share. And
Yeah, I assume if we get a data file like that last sample example there, we'll be able to download it.
sorry, what's that?
I assume if we had on the test problem similar to that last one, we'd
Yes,
be able
you need to be able to download. Exactly, it would be good
Right?
to download that. I will look into that for you because at this point, I can't say for certain, but ideally it should, I mean, in a test, you don't want to have to be taking all that data and then re-entering it into an Excel file. Yeah.
It's just pointless, Yeah.
Yes, I totally agree with you. All right, let me see here. I'm saying, just trying to figure out why I'm not seeing, why you guys are not seeing this thing. Let me try. This is really getting me upset now. I'm gonna try this guy. I think we're good now. Yes, you're seeing that for sure.
Yeah, we can see it.
Right, because I definitely had to reboot the iPad because most times I just put it to sleep. I never really shut it off, so it probably needed to sleep and then wake up. Okay, good. So we have here. Let me just give you a question that we will actually try to solve for you. Now, in those PowerPoints, there are a couple of examples in there, and in MindTap, they usually do a couple of small examples. So I'll leave those examples, but now I'll try to grab some from the textbook. So if you have your book with you, I think the first question I wanted to look at was my notes right here, is a question number 5 from chapter 10. So I'm going to, just for you to see that, I'm going to bring up MindTap, and we're going to use the electronic textbook. That way I could share it with you. And so we know this works now, which is good. And I'm going to bring up, so if you could bring up your electronic text in MindTap, or if you have a physical text, that's fine. Just going to log into my account. And go into the course. So we're going to be able to read the question that we will work out. Sorry. Textbook, chapter 10. So if you're following along with me, you could go to chapter 10 in the textbook. And I wanted to look at a question number 5. Let's see, exercise and applications. Let me make sure I'm looking at the same question. Okay, I think I see it. All right, so I could share with you if you don't have a book in front of you, so I'll share my screen. And where's my MindTap? Here we go. All right. So you can see my book here, I presume. Number 5. Can you see that?
That's from Mind App, yeah.
Yes, I'm looking at the electronic textbook.
Okay.
So number 5. So let's just kind of go through this a little bit together here. So this question will deal with the case where we are interested in the difference between two population means, but the population standard deviations are known. All right. So and again, I think Callie, to your question about sometimes we understand the mechanics, but knowing which formula to choose. Like, so in this case, you could have 3 different scenarios where we're looking at difference between population means. One where sigma is known, one where sigma is unknown, and one where we have match pairs. So being able to identify those 3 different scenarios would be important. So let's see what's in this question that would help us know that this is the first scenario where we have sigma 1 and sigma 2 known, and therefore we would use Z, right? So we're told USA Today reports that the average expenditure on Valentine's Day is average expenditure is $100.89. The male and female consumers differ in the amount to spend on the amount they spend. The average expenditure in a sample survey of 40 male, so we're told 40 male, was $135.67. The average expenditure for females, 30 of them, was $68.64. Now it says here, based on past surveys, so they're basically talking about population, even though they've done surveys, but that is going to kind of allude to, well, we've accepted that as the population values. Standard deviation for male consumers is assumed to be 35, and standard deviation for female consumers is assumed to be 20. You see, if it had said, based on the 2 surveys that we have, then we could say the 35 and the 20 are S1 and S2. But because it said based on, in the past, we have to treat those as if they're the population standard deviations. So that would be like sigma 1 and sigma 2 unknown. All right? So first part of this question here is, what is the point estimate of the difference between the population expenditure for males and females? The point estimate, remember the point estimate is the value that you get from a sample. So because we are interested in x bar 1 minus x bar 2, and mu1 minus mu2, or the difference between males and females, then our sample estimate or point estimate must be x bar males minus x bar females. All right, so let me do this. That's not what I want to do. I'm going to share using AirPlay. Okay, so I'm just going to going back to this particular question, we are interested in, if we go to, let me just get a clean page here. All right. Okay. So in this particular question, we're basically interested in the difference between men and women, all right? And we're interested in whether or not there's a difference between them, or whether or not men spend more than women. Let's see. So in this case, mu m minus mu W. Are you seeing that at all? Because I'm seeing, it's almost like,
we're not seeing that. If you're writing, we're not seeing you writing.
okay, yeah, because I noticed that my screen looked frozen a little bit. It has been paused. Why did it pause? I'm going to try again. Play, play. And okay. So this is what we're interested in, the difference between the population mean for men and women. So if we were to kind of just sketch that, it's almost like we have this mean for men, standard deviation for men, and then the mean for women, and standard deviation for women, right? And we're asking, we're interested in the difference between those two groups of individuals. So what is the information that we were given? We know that the number of men surveyed was 40, and the number of women surveyed was 30. We also know that we got a sample mean for men of 135.67, right, dollars. And we got a sample mean for women of $68.64. So that's the information we have, but we also are told, based on past surveys, so we'll treat that like population values. Standard deviation for men was considered to be 35. Standard deviation for women was considered to be 20. So the first question is asking us, what is the point estimate of the difference between the population mean expenditure for males and the population mean expenditure for females? What's the difference? So we're interested in that difference between mu M and mu W. Well, what would estimate that for us? The estimate of that would have to be X bar M minus X bar W. They have to look similar because remember that this is a point estimate of the true population difference. So if we're taking the mean for women from the mean for men, we must take the sample mean for women from the sample mean for men. So keep it consistent. And in that case, it would just be the 135.67 take away 68.64, and that answer should be equal to, if I look at my notes, $67.03. $67.03. So just based on the point estimate, it looks like men are spending more on women, which is interesting, right? It almost seems to suggest that Valentine's Day is more about women than it is about men. I don't know how you know what your view on that is, but it seems like the men are having to spend more. Men have to buy flowers, chocolates, gifts, just tease it. So based on the sample data, it seems that men are spending more money. Now, second part says develop a 99% confidence interval, right? But that's what we want to develop. But what is the margin of error? So if you recall, margin of error in any confidence interval is the part that comes after the plus or minus. So for this situation right here, the confidence interval, 1 minus alpha times 100% confidence interval would be given by X bar M minus X bar W. Let's put that in brackets, plus, and then Z. Why am I using Z? It's because the population standard deviations are known. Sigma 1 squared over N1, sigma 2 squared over N2. And so all I would need to do is to substitute the values. So that's the point estimate. Point estimate is this piece right here. And this part right here is your margin of error. So remember, the margin of error has two parts to it. This part right here, which is our critical value, and this part right here, which is our standard error. So the critical value times the standard error equals to the margin of error. So for this particular question, if we wanted to calculate the standard error, then we would have to take the values that we had before. We were told 35 and 20. So 35 squared over, I believe it was 40 males, plus 20 squared over 30 females, and take the square root of that. That will give us our standard error. And the answer to that is 17.08. Right? The last thing we want is the confidence interval. Well, remember, the confidence interval is the point estimate plus or minus z times the standard error. In this case, we already know that our point estimate was $67.03. So a 99% confidence interval. What is the Z value for a 99% confidence interval? It turns out that that would be 2.58 if you want to round it off to 2 decimal places, or 2.576 or something like that. So in that case, we would take the 67, that's the value of x bar m minus x bar w and 3 cents, plus or minus the Z value, which is 2.58, plus or minus, sorry, times the standard error, 17.08. When we put it all together, it turns out that that is 67.03. Oh, I made a mistake somewhere. I know what my mistake is, that I wanted the margin of error. The margin of error is 17.08, but I do not have the Z value in here. That Z value here. So my margin of error is equal to 2.58 times the standard error, and that gives us a 17.08. So sorry, my bad, I made a mistake here, in which case I have to remove this, because I have already calculated the margin of error. So this is plus the 17.08. All right? And that turns out to be that mu of men minus mu of women. If I add 17.08 to that value will give me 84.11. And if I subtract 17.08 from 6703, that value will be 49.95. So how am I interpreting that? I'm interpreting that as the difference, the 95% confidence interval, 99% confidence interval, not 95, 99% confidence interval for the difference between the mean amount spent by men and women, the difference between that is somewhere between $49.95 and $84.11. So in other words, because we're subtracting mu W from mu M, and both of these values are positive, there's no zero in that interval. So if there's no zero in the interval, it means that the two things cannot be equal. One has to be bigger than the other. So since both values are positive, then in that case, mu M, we have evidence that mu M is larger than mu W. Is larger than mu W. Because for any value in that interval to be positive, mu M must be the larger one. All right? And so therefore, we have evidence that men spend on average between $49.95 and $84.11 more than women on Valentine's Day. So that's that particular question that takes care of difference between two population means when the standard deviations are known. Now, what if we want to test a hypothesis using this very same data? We want to test the hypothesis that there's a difference between, or let's not just say there's a difference. Why don't we just test that, let's just test that there's a difference between them. There's a difference between the amount spent by men and women on Valentine's Day, using the very same data. So how can we frame that as a hypothesis test using this very same data? Okay, no problem. Kali's leaving, so Kali, no problem. I understand. You have to leave. All right? No problem. Take care. I will finish this up, and we'll take it from there.
Thanks. Have a good night. Thanks.
You too. Okay. So, Ken, it's just me and you.
Just us.
You have a whole class all to yourself. I don't know why people aren't attending the classes. I'm not sure why. Maybe because they go to the recording afterwards. I don't know. All right. So
maybe they're all sorry,
I don't know if there's a night that would work better for most people. The other thing too is that the course outline have like I said, the video link, so probably some people figure that's enough for them. I don't know. It's fine. Let's do this as a hypothesis testing question.
Yep.
All right. So, if we wanted to test if let me see. Did I lose my connection?
Yeah,
I did. Okay, it's gone. Let's put it back on again. Okay. All right. So here we go. So in this case, we will have the hypotheses. Step one. So what we're going to do is use exactly the same data and just answer the question with a 1% significance level. Since we have a 99% confidence interval, I'm going to use the same significance level. For 1% significance level, is there a difference between those two mean expenditures, right? So hypotheses, HO, HA, or H1. So if we're asking if there's a difference between them, what we would then be saying is that the mean for men minus the mean for women is not equal to 0. If there is a difference between them, then the two of them can't be the same. It has to be the difference is 0, non-zero. But then our null hypothesis, we will state, okay, let's assume that the difference is 0. All right, so that's step one. Step two, we need a test statistic. How are we going to measure whether or not we have sufficient evidence to support the alternate hypothesis? So we need the test statistic. Because sigma 1 and sigma 2 are known, then it would be Z is equal to, remember, sample point estimate, so X bar, we have to keep it in the same order, X bar M minus X bar W minus mu M minus mu W divided by the standard error, sigma M squared over NM, sigma W squared over NW. So that is a test statistic that we will use. Now we already have the point estimate. This will get its value from the null hypothesis. And then we already have the standard, well, we have the information for the standard error. We'll figure out what that is. I think I could figure out what that value is. So let's look at step number 3, which is our decision rule. Now, if we're using the classical method, the critical value method versus the p-value method, if it's p-value, then we don't really have to do much at this stage. We just need to state 3, the decision rule. So alpha is 0.01, right? So we would say if p-value is less than alpha, 0.01, we will reject the null hypothesis.
Is alpha 0.01 or is alpha, should we work with half alpha since it's two-tailed?
No, alpha, okay, so what happened is that the confidence interval was 1 minus alpha, right?
Right, yeah.
Which was 0.99,
right.
which means alpha is what's left, the 1%.
Right, okay.
Right, so what will happen now, because this is going to be a two-tailed test, we're going to have to split it now to alpha over 2 for the two-tailed. So this, I'm just doing p-value right here, but if we were doing the critical value approach, then we need to figure out what those critical values are, right? So in that case, what we would do is we would say, here's the rejection region in the tails, and these rejection regions would be alpha over 2, right? In which case it's 0.005, 0.005. When I divide 0.01 by 2, it gives me 0.005. Make sense?
Yeah.
When we look at the Z table, for 0.005, this should give us 2.58, negative 2.58. So if we look at the Z table, so which means that in terms of the critical value approach, if the Z value is greater than or equal.
Z critical is plus or minus 2.58.
Sorry, what's that?
Z critical is plus or minus 2.58.
Yes, correct. Yes, you got it. And so if Z is greater than 2.58, that means we're in this part of the rejection region. Or if Z is less than negative 2.58, we will reject the null hypothesis. So that case, we're down in the bottom part of the rejection region. So that would be the critical value approach, or the p-value approach. All we need to do is to just state this, which is why I like the p-value. You don't have to go through all of that. Compare that, I just blocked off here with this whole diagram below. But then they give you exactly the same answer. Once you understand it, you get exactly the same answer. All right?
Yeah.
So step 4 now, we have to do the analysis on that. So we would have to take Z is equal to, and we did get 67.03 as our sample difference, minus 0 from HO. And then we need the standard error. Now, I know that the margin of error was 17.08. So if I divide 17.08 by 2.58, I should get decent. I'm just trying to do a little shortcut here. I'm having to calculate this all over again. 17.08 divided by 2.576. Okay, so it's 6.63. You could actually verify that by just going and doing the calculations, but that's 6.63.
The 0 for UN minus UM. That's based on the test statistic or the hypothesis, right?
It is based on H0.
Yeah, so that could be another number besides 0.
That's right. It could be another number. What if I was testing that? What if we had claimed that men spend $50 more, right?
Yeah, 260 is a zero.
And that's right. And then now I'm interested in testing whether or not men spend $50 more or different from $50.
Yeah.
Then in that case, I will put, instead of 0, I'll put 50. Yeah. Okay, good. So if I divide 67.03 divided by 6.63, that gives me 10.11. That's a pretty big Z value. So given that our textbook doesn't really have, unfortunately, the exact value, you could use Excel and get the exact value, but for our textbook, so our p-value would be this. So we get the Z value right here, 10.11. If I were to just, for now, just draw this diagram, so we know that our critical value is 2.58. And as long as we're in this region right here, we're rejecting the hypothesis. So 10.11, we could just draw it somewhere down here, right? Which means that the p-value, that little piece right here is only half of the p-value. The same way that this was alpha over 2, this little piece would be p-value over 2. It's only half the p-value. Where's the other half? The other half is down here, negative 10.11. The other half is down here, p-value over 2. So whenever it's a two-tailed test, we must take this area multiplied by 2. All right? So we got to figure out what's the area associated with this. Well, we know that the area associated with this in our tables, the best we could find is less than 0.001. Which means our p-value will be twice that, right? So p-value would be twice less than 0.001, which is basically less than 0.002. So since the p-value is less than 0.002, we know it would be less than 0.01. And therefore we could reject the null hypothesis. So if we're doing the p-value approach, we will compare this value to 0.01. If we're doing the critical value approach, we'll compare 10.11 to 2.58, right? So in both cases, we get exactly the same answer, same conclusion, which is essentially, you could say, since 10.11 is greater than 2.58. And I won't just say greater, I could even say much greater by putting 2 of them. We have strong evidence of a difference between the mean expenditure of males and females for Valentine's Day. Okay, so that's the conclusion. And then, of course, can we commit an error? The answer is yes. What kind of error? Because we reject the null hypothesis, there's a possibility of type 1 error. Why? Because type 1 error is rejecting the null hypothesis when it is true. So the first thing you must do is reject the null hypothesis. And then either you're correct or you commit an error. And that error that you can commit is type 1 error, because type 1 error by definition is rejecting the null when it's true. Since we rejected the null, what if it were true? Then that's type 1 error. If we reject the null and we're supposed to reject it, then we've done the correct thing. But in our analysis, we are only taking, what kind of risk are we taking? Less than 0.002. That's our p-value. The p-value is the actual risk of us being wrong. That's less than 0.002, less than 0.2% chance that we're wrong. So it's a pretty good gamble. That's kind of what this is telling us there. P-value measures for us just how much of a chance we're taking in committing type 1 error. And so less than 2 cases in a 1,000 is a pretty decent, you know, gamble, is what that's telling us. All right?
Yeah.
Cool. So if we were to pretend with this problem that sigma 1 and sigma 2 were unknown, but using the same data, just so that we don't have to go and do a whole bunch of different data, but just focus more on the concepts. If we had to just change the idea and say that the standard deviation of 35 and 20 were obtained from the sample values that we got. In that case, the population standard deviations would not be known. We only have sample standard deviations. We now have to go to T. So let's just look at that. So let us assume that S1 is 35 and S2, or I should say S men and S women. It's 20. So that is sigma 1 and sigma 2 are unknown. So what would change for us? Well, in terms of the confidence interval, we would use T. Why? Because sigma 1 and sigma 2 are not known, so we would use x bar m minus x bar w plus or minus T. Alpha over 2 degrees of freedom, Sm squared over Nm plus Sw squared over Nw. That's what we would use. What's the big problem for us? Our degrees of freedom. We have a crazy formula that I could never remember. And the main thing is just for you to recognize that now you're going to have to use this formula to calculate the degrees of freedom. So put it in Excel, right? And it looks something like this. You have a numerator that says, what's this? Is x1 squared over n1 plus s2 squared over n2. Then you take that and then you multiply 1 over n1 minus 1, s1 squared over n1 plus 1 over n2 minus 1, s2 squared over n2. So you do that calculation and you round that up to the nearest integer. So whatever we calculate for this particular problem, we could get the degrees of freedom, look up that degrees of freedom and the alpha over 2 and find our T value. Once we find our T value, so I could tell you that it will be bigger than 2.58 because the T values tend to be bigger than the corresponding Z values. So it might very well be like 2.6 something or 2.7 something, I don't know. And in which case, what it does, it makes the interval larger, all right? So I want you to just understand that it's the same process. The only thing now is to recognize that we're going to have to use T instead of using Z. Does that make sense?
Yep.
And then if we're doing the hypothesis test, then everything remains the same except that, again, we would have to use T is equal to x bar m minus x bar w minus mu m minus mu w over S1 squared over N1, Sm squared over Nm plus Sw squared over Nw. Well, actually, what's interesting is that this will still be 10.11. Why? Because, I mean, I just called the same values S instead of sigma, but all the numbers are still the same. This will be 0, this will be 67.03, and then this will be 6.63. So nothing will change. The only difference is that now we will be comparing that 10.11 to whatever the critical T value is that we get. The T value, the T alpha over 2 degrees of freedom, with this degrees of freedom calculated, which I believe will be about 2.6 something or 2.7 something. Whatever that turns out to be, 2.6 whatever or 2.7 whatever, this number is going to be much greater than it. So we will still have our same conclusion, even though we assume now that the population standard deviations are not known, but we use the sample values to give us our best estimate. Yeah. So in other words, the methodology stays the same, except for that we need to now recognize that we're using the T distribution instead of using the normal distribution. So that covers the first one, which is, so far, finding a confidence interval and hypothesis test when sigma 1, sigma 2 are known. Second case, when sigma 1, sigma 2 are unknown. Let's do an example now, and then that would be our third example to cover the 3 areas with match pairs. So let me find an example for you now with match pairs. And then once we finish that, then we would have covered the materials for today. So I will look at, yeah, go ahead, please. Okay, I'm just going to pick a question here. Let us look at question number 25. So if we're in the same chapter, I'm going to go to question number 25. And if I go back to chapters, I'm sorry. And I want to look at difference between population match pairs. Okay, so here we go. Problem 25.
One of the college board SATs?
The one that, yes, that's it. Got it. So if we look at that question now, let's see what will allow us to recognize that this is a match pairs question. Because that's really, like I say, where students seem to have some of the difficulty, yeah? Is identifying which question, what kind of question we're dealing with. So the College Board SAT entrance exam consists of 3 parts: math, writing, and critical reading. Sample data showing math and writing scores for a sample of 12 students. So math and writing scores for a sample of 12 students follow. And notice that it doesn't give us all the data here, it just shows us 7 of the values, but it shows us for student number 1, their math score and their writing score. Number 2, their math score and writing score. Number 3, math score and writing score. So clearly, those first 2 values are matched to the student number 1. Second 2 are matched to student number 2. So that's a match pairs question when we look at that. And the question is asking us, at a 5% level of significance, test for a difference between the population mean for math scores and writing scores. So in other words, test whether or not there's a difference between the math scores and the writing scores. Are they the same or are they different? So that's a hypothesis test. And because we have a single sample of 12 students, but each of them giving us 2 scores, then those values are matched. What that allows us to do is to take that problem and distill it down to a single sample problem. So let's do that and see what we get. So the way in which you would approach that is that you would need to create a third column. So I'm just going to grab some values here. I won't write down all of the 12 values, but I just show you what we're going to do with it. So you'd have in this question number 25 here. Okay, time for new color. My pen. So we would have student, and then we would have their math score and their writing score, right? Student number 1, 2, 3, 4, up to 12 student. This person got a 540 in math and a 474 in writing. Next one got a 432. Next one got a 380. 528 and 463. So what we're going to do is we're going to calculate the difference between the match pairs. And you could do math minus writing or writing minus math. It don't matter. You just need to know which is which. What did you actually do? So in this case, what I like to do is to look to see which values are bigger and take the smaller one from the bigger one, because I don't like working with negative numbers, right? So it looks like the math ones seem to be generally bigger right now. So I'll take my differences will be math minus writing. And let me just put, yeah, so so for each one of them. So in that case, the first one is 540 minus 74. You have 26 and 40. That looks like 66, I believe. Yes, that's a 66 difference. And then the next one would be 52. The next one would be 65. Okay, so we just keep doing that until we get all of the differences. So if I were to write them all out for you, for this particular question, the differences are as follows: 65, 38, negative 38, 28, 28, negative 24, 50, 40, negative 5, 31, 55, and negative 20. So those are the 12 values. So n is equal to 12 for this question. And so with those 12 differences now, what we're going to do is to calculate the average difference, which is basically the sum of all of the differences divided by n. We must calculate the standard deviation of the differences. Why? Because now we're going to test the hypothesis that the difference between math score and writing score are different versus they're not different. And so because we have the match pairs and we take the differences between the match values, when I average those differences, that sample average is really an estimate of the difference between the math and the writing score. So what that turns out to be, if you add it all up, is 300 over 12. It turns out to be 25. So that 25 is the average difference. That's our estimate. Our estimate of the average difference between the mean for math and the mean for writing. Okay, so what we're doing is we're defining that as a mean difference, mu d, which is just the difference between those two. We're treating like a single problem because of the match pairs. All right, and that d bar is our estimate of the mean difference. Now we have to go and calculate the standard deviation, and you may recall I gave you guys a shortcut formula. The book uses this formula right here, which I don't really like because to me it's just extra work. But the book will give you di minus d bar squared, and then you have to take n minus 1, but then you have to sum all of that up and take the square root of it. That would be SD. But what I showed you guys in the formula sheet is that it's a little shorter if you did it that way, this way right here, is to take, I have the DIs, and the sum of the DIs in this case is 300. If I take each DI and I square DI squared, so 66 squared, 52 squared, etc. If you have that in Excel and you just square those values and you add them all up, you will get the sum of DI squared. Now my notes don't have the sum of DI squared because they do it the old way, old-fashioned way, which I don't really like that much. But if you use those values, whatever that is, and you could calculate SD as the sum of DI squared minus the sum of DI all squared over n, and we divide the whole thing by n minus 1. It looks more complicated, but it actually requires less work, than doing this one up here. But the book uses this model. But you get exactly the same answer. So it turns out that if you calculate SD from the data that we have, your standard deviation will be 37.05. So I have the standard deviation. I have the sample mean difference of 25, right? Sample mean difference of 25. I could do a few things with that. So let's see what we could do with this data. And we know the sample size is 12. So here are some of the things we could do with that question. What did they ask us for? Test for the difference between them. And then part B asks for what is a point estimate, so a confidence interval, right? So let's look at the 5% level of significance, test for the difference between those two. So we're going to do that. So alpha is equal to 0.05. Test for a difference between mu m and mu w, right? So first one's hypotheses, HO, HA. So what we'll do is we'll define mu m minus mu w as mu d, the difference. So mu d, so we wanted to, that there's a difference between them. So we'll say mu d is not equal to 0 versus mu d is equal to 0. So if mu d is not equal to 0, it means that either math is higher than writing or writing is higher than math. At this point, all we care about is that they're different. Step 2, test statistic. So is this a T or a Z? Because we are testing a hypothesis for population mean. So if you look at our data, first of all, our sample size is small. And do we know the population standard deviation in this case? No, we only know sample standard deviation, which we calculate from the sample of 12. So since sigma is unknown, then we use T. So T is sample estimate. In this case, it would be D bar minus population mu D over the standard error, which is S over root n, but we just put SD to denote the standard deviation of the differences. So that's our test statistic right here, right? And the mu D will get its value from HO. So that's our test statistic. Our decision rule, it told us 5% level of significance. So let us so number 3, decision rule. So if we do this, this is a one-tail test or two-tail test? We have an HA not equal to.
Yeah.
So that would be two-tail, right?
Yeah, two-tail.
Okay, exactly. And the alpha, which is 0.05, must now be divided between both tails. So which means that we have alpha over 2 over here, alpha over 2 over here. Because alpha is 0.05, what's half of 0.02? Sorry, 0.05 would be 0.025. Cool? Half of the 0.05 in each tail, correct?
Yeah.
So to find our critical value, that t value is the t value for 0.025, but we need the degrees of freedom. df is n minus 1. In this case, 12 minus 1, which is 11. So our critical value is t 0.025, 11 degrees of freedom. And we can look that up in the table. I think I might have it here already. It turns out that it is Oh, the book uses the p-value approach. It didn't give us the critical value approach. Let me look up the table and get it. So I need 0.02511. I should have that here. If you have your tables, you could check it out quickly. T 0.025. In the tail, 11 degrees of freedom. I get 2.201.
I don't have my tables.
No problem. I could share it with you.
Oh, it's okay. Okay, I got them here.
Okay, no problem. So if you look up the area in the upper tail, area in the upper tail is 0.025.
Yeah.
And then you go down to 11 degrees of freedom, it's 2.201.
Yeah.
So that's our critical value. So T is 2.201, negative 2.201. So that's step 3. Or the p-value, if we were just using p-value, it would just be that if the p-value is less than 0.05, then reject the null hypothesis. So that what I showed you was the critical value approach, or we could say, or if p-value less than 0.05, reject the null hypothesis. Step 4, the analysis. So we already know that our t value is d bar minus mu d SD over the square root of n. So the average that we got, we said was 25 minus mu d, which is 0 from the null hypothesis. The standard deviation was 37.05 divided by the square root of 12. It turns out this is negative 2.34. Why negative? Now I'm just looking to see, that's just 2.34, sorry, not negative 2.34. 2.34. Okay, and so 2.34 is our t value. Remember, our critical value is 2.201. So it's just a little higher than that. So it exceeds it, which means that we are in the rejection region.
Yeah.
And so our conclusion will be that we have enough evidence of a difference between the mean math scores and the writing scores. So that's what we'll conclude. So for 5, our decision will be, since 2.34, sorry, is greater than 2.201, we will reject the null hypothesis, and we conclude there is a difference between the mean math and writing scores. Okay, can we make an error? Can we be wrong? We can be wrong. What kind of error? Type 1 or type 2?
Type 1.
Type 1 error, precisely, because type 1 error is based on rejecting the null hypothesis. Since we rejected the null hypothesis, the only error that we could commit is type 1. All right? So that would be the error. If we wanted the p-value associated with this, so this should be interesting. Whenever you find in p-value the t-distribution, it's a little tricky. So let's find the p-value so that we know how to find p-value with t-distribution as well. All right. So since we know our value, our test statistic is 2.34, the p-value, because the two-tailed test, would be twice the probability of t being greater than 2.34. So what we have to now do is to try to see if we could find 2.34 in the table. If you go back to the table under the 11 degrees of freedom, when the area in the tail was 0.025, the t-value was 2.201, which is what we use in the problem, right?
Yeah.
But to get 2.34, we have to keep going to the right.
Right. Yeah.
Which means that we will land somewhere between 0.025 and 0.01, precisely.
And
So
that twice that because of the tail?
So we now have to actually multiply it by 2, which means that we'll be somewhere between 0.02 and 0.05.
Yeah.
Yep.
Yes.
In which case, we're still, if we are between 0.2 and 0.02 and 0.05, we are still smaller than 0.05.
Yeah.
So then we would reject the null hypothesis. So in this case, this is, let me see what's the best way to write that. This is twice 0.01 p-value over 2, half the p-value, 0.2, and 0.025. So if I multiply that by 2, it takes away the 2 under the p-value, so it will be that this is 0.02 p-value is less than 0.05. So you can see here where it satisfies the decision rule. The decision rule says reject the null hypothesis when the p-value is less than alpha. That 0.05 is alpha. And so we've just shown that the p-value is less than 0.05, in which case we would reject the null hypothesis. Yeah. And that, so reject HO. We have the same conclusion. I won't bother to rewrite it, but we have the very same conclusion. So we actually just did a hypothesis test with that. You could actually do a confidence interval with exactly the same data, because remember that we did confidence intervals for population mean. So all we're doing here is the same confidence interval for the difference between the population means, but is now based on a single sample. So our confidence interval formula would look like this. So a confidence interval, and that's our last thing, confidence interval, would basically be point estimate plus or minus critical value times the standard error, S over root n. That's kind of similar to the one that we did before, TS over root n. So what's the difference between them? Only thing is that we're using d bar to represent the average of the differences. But that's an average as well. In fact, some books use this, which I prefer, x bar d.
Okay.
Which is basically means the average of the differences, and then it looks more like what we've done before, right? SD over square root of n. So you're seeing the same t, instead of SSD, and instead of x bar d. But we got to stay consistent with the textbook, and so instead of x bar d, they're denoted by d bar plus or minus t alpha on 2 degrees of freedom, SD over root n. And since we had our d bar already, what was our d bar? Was 25 plus or minus 2.201, and this was, I think, was 37 point something for 37.05. 37.05 over the square root of 12. If you use that, you will get a confidence interval for mu d. I'll let you finish that up at home. That confidence interval for mu d, and you should end up getting a confidence interval where the 0 is not present in the interval. When 0 is not present in the interval, that means that you do have evidence of a difference. Whenever 0 is present in that interval, you don't have evidence of a difference. I don't know if I could try to make this a little clearer for you as our very last point. Let's put it this way. If I drew a line, and that is the 0 point, That's a positive difference, that's a negative difference. Let's say this line represents where the value of mu1 minus mu2 falls, right?
Yeah.
So if mu1 minus mu2 is positive, if both of the limits of the interval falls on this side,
right,
then that means any value in that interval is positive. I'm on the positive side, which means that on this side here, mu1 will be greater than mu2 if the difference is positive. On the negative side, what if both intervals fall on the negative side? That means the 0 is not in the interval. If both of them are negative, it means that mu2 must be the larger one, right? So mu1 is less than mu2. But what happens when we have an interval that goes across the 0? This part of it, on the negative side, is mu1 is less than mu2. But there's a part of it that is on the positive side, which means mu1 could be greater than mu2. And at the point where it's 0, if the difference is 0, what does that say? Mu1 is equal to mu2. There's no difference between them.
right.
So whenever the interval crosses over that 0 line, it is possible that the two means can be the same. So that's why we say we don't have enough evidence of a difference anytime the interval for a difference contains a 0. Yeah? So that helps to kind of just understand how to interpret the confidence interval. If I have my difference, mu d, is between 2 and 6, both values are positive, that means that there is a difference between them. If I have between -4 and say -2, then any difference here is negative, right? But then if I have between -4 and 6, then the 0 is in the interval.
Okay.
So it's possible that mu1 could be equal to mu2.
Okay.
And so since it's possible for them to be the same, I cannot prove that they're different because it's possible for them to be the same. And that's the interpretation of that. So that covers the 3 areas, which was basically testing for difference between population means when sigma 1 and sigma 2 are known, testing for difference between means when sigma 1 and sigma 2 are unknown, and then testing for the difference between sigma 1 and sigma 2 when we have matched pairs. And matched pairs are quite useful to help us reduce what we call the sources of variation between the two samples. So as I gave the example about two groups of people, separate groups of people trying method number 1 and method number 2, then it could just be that one group had better workers and so on. So there could be differences between the two groups. But if it's the same group of people trying method 1, then trying method number 2, you're eliminating the differences between the two groups because you're using the same people in both cases. And so your results tend to be a lot more precise when you do a match pairs experiment in that case. All right?
Yep.
All right. So that brings us to the end of our lecture for today. I will look into those issues that you talked about and see if we could address any of those before the next test. Okay?
Yeah. Yes, thank you.
No problem. You have a good night.
You too.
Okay, all right, bye-bye. See you on, I will send a notice about Tuesday, and we'll try to do the go back to the lecture on Tuesday and hosting some office hours on Thursday.
Okay.
All right, take care. All right, bye-bye.
Good night.
Night.